Welcome everyone, myself Dr. Deepmala Gupta, Assistant Professor, Department of Chemistry, School of Science, UP Raj Tandon Open University, Prayagraj. Today we will be starting with Unit 2, Mechanism of Organic Reactions and Reaction Intermediates, Module 4. Course code UGCHE-102, course title Organic Chemistry 1, Basic Organic Chemistry. In the last lecture we will talk about curved arrow notation, drawing electron movements with arrow, half-headed and double-headed arrows, homolytic and heterolytic bond breaking, and types of reagent like electrophiles and nucleophiles. In module 2, we talk about types of organic reactions like substitution reactions, addition reactions, elimination reactions, and rearrangement reactions. In module 3, we talk about reaction intermediates, carbocation, carbon anions, free radicals, arenes, carbenes, and nitrines. Today we will be continuing with energy considerations. Chemical reactions may be regarded as equilibrium process, the point of equilibrium being dictated by the relative energies of the reactants and the products. Reactions which do not proceed at all are also equilibrium processes for which the equilibrium constant has a value near zero. A chemical reaction proceeds when the products are more stable than the reactants. The equilibrium constant of a reaction depends on the two factors, enthalpy change and entropy change. Enthalpy change is represented by delta H, and which is the quantity of heat released or absorbed when a mole of reactant converted into a mole of products. And the entropy change is represented by delta S, which is a measure of the energy consumed or released in the reaction to create more order or disorder in products relative to reactants. When entropy change is taken with the absolute temperature, it gives the free energy change according to the relationship. Here delta F is equal to delta H minus T delta S. Delta F is free energy change, delta H is the change in enthalpy, T is absolute temperature, and delta S is entropy change. Here it should be noted that a reaction proceeds in the forward direction only when delta F is negative. That is, there is overall release of energy. On the other hand, a positive delta F indicates that the reaction has a tendency to go backward. Since entropy is a measure of the degree of freedom of a system is most stable when it has maximum entropy. When all the substances are in their standard state. Standard states means the temperature is at 25 degrees centigrade and the pressure is 1 atmosphere. Then the equation may be written as delta F0 is equal to delta H0 minus T delta S0. Here delta F0 is the free energy change at a standard state. Delta H0 is the enthalpy. Here delta F0 is the free energy change at a standard state. Delta H0 change in enthalpy at a standard state. T is absolute temperature and delta S0 is entropy change at a standard state. Here the subscript 0 is used to denote standard states and delta F0 is the difference is a standard free energies of products and reactants. The relationship between the equilibrium constant K and delta F0 is given by the following expression. Here delta F0 is equal to minus RT ln K, where ln K is natural logarithm of K delta F0 free energy change at standard state, and R is gas constant and T is absolute temperature. From the previous discussion, it is clear that a reaction will proceed only when the products are more stable than or the same order of stability as the reactants, and there is a suitable pathway between reactants and products, that is the rate constant K is favorable. There is a characteristic rate constant associated with every reactions. The larger the value of K, the faster the reaction. Now, the question arises as to what factors make one rate constant larger than another. So, two important theories explain the difference in rate constant are collision theory and transition state theory. Now, collision theory. According to collision theory, molecules react only when they collide. Thus, information regarding the rate of reaction can be gained by knowing the number of collisions taking place per unit of time. Obviously, the frequency of the collision will increase by increasing the concentration of the reactants. The frequency of collisions also depends upon molecular motions, which in turn depends upon the temperature. It is expected that the rate of reaction will increase with a rise in temperature. However, the rate of reaction does not depend only on the frequency of the collisions, as it has been found that only 1 in every 10 to the power 15 collisions leads to products. This has been explained by assuming that collision between molecules will be successful only when they contain at least a minimum amount of energy called the activation energy and represented by EA. Activation energy is required even for a thermodynamically favored reactions, as energy is needed for breaking the bonds in the reactants before new bonds are formed in the products. Thus, there is a geometrical arrangement of atoms possessing higher energy than that of either reactants or products. Reactants have to pass through this highest energy state called an activated complex before their conversion to products as shown in figure. And this figure shows collision theory energy diagram of a typical reaction, and this is the reactant and this is product, and here EA is the activation energy. However, there is a further limitation, that is the colliding activated molecule must be effectively oriented with respect to each other for a successful combination. In other words, the activated molecules must be suitably oriented to react when they collide. This limitation is referred to as probability factor and is represented by capital P. The rate is expressed as rate is equal to Pz exponential minus Ea upon RT. Here P is probability factor, Z is the number of collision per unit, Ea activation energy, R is gas constant and T is absolute temperature. Now, transition state theory. The transition state theory of reaction has been found to be more useful in understanding the mechanism of organic reactions. It takes into account the energy changes of the reactant molecules as they are brought together and are ready to collapse into products. Like collision theory, This theory also assumes the existence of a transition state through which reactants must pass before their conversion to products. The rate of reaction depends on the rate at which the reactants reach the transition state instead of the frequency of collisions as seen in the collision theory. The species is in equilibrium with reactants and hence its concentration is determined by an equilibrium constant denoted as KH, which is related to the enthalpy of activation. Here delta F0 is equal to delta H has minus T delta SS, which is equal to minus 2.303 RT log KH. Where transition state is denoted by H, F is the free energy of activation, delta H is the heat of activation, and delta S is the entropy of activation. Let us discuss transition state theory by considering a general reaction without involving an intermediate. Here A react with BC gives AB and C. It has been shown by making certain approximations that a minimum activation energy is required when A approaches BC along the bonding line of BC and on the side remote from C. The bond AB begins to form whereas bond BC begins to stretch. During the reaction, each bond may be regarded as a partial one with both AB and BC bond distances greater than those in the product and the reactant. However, the amount of energy released during the partial formation of bond AB is less than absorbed by the corresponding partial separation of the bond BC. As a result, the energy of the system begins to rise with the process of bond transfer. The rise in energy finally reaches a maximum where the system is least stable, followed by a fall. At the end of the reaction, the bond BC has been completely replaced by the bond AB. The transition state is the state of highest potential energy acquired by the reactant during the transformation. The system at this point is also called an activated complex. It possesses a definite geometry and charge distribution. However, due to the associated high energy, it is highly unstable and cannot be isolated. The activation energy, besides other factors, depends upon the strength of BC and AB bond. The stronger the BC bond, the greater will be delta F hash, and conversely, the greater the strength of AB bond, the lower is free energy change. The energy changes that accompany a complete reaction are conveniently represented in the form of an energy diagram with free energy plotted against the pathway of the reaction called reaction coordinate as shown in figure. Here, this figure shows energy diagram for single step reaction, and here delta F has represent the energy barrier. The greater the height, the slower will be the reaction, and delta F0 represents the difference in standard free energy of the reactant and the product. It is a thermodynamic quantity and does not affect the rate of reaction. Now, multi-step reactions, free energy diagram. These reactions usually involve the formation of one or more intermediates, and there are two or more transition states, each with higher energy than that of the reactants, intermediates and products, represented by an energy profile diagram of the following reaction. Here A and B is reactants, which gives intermediate I, and this gives product, and this is the slow reaction, and this the conversion of intermediate to product shows fast reaction. The deeper the depression, the more stable will be the intermediates, while a shallow depression in the energy curve indicates a less stable intermediate. Although there are two transition states, each with an higher energy than that of the intermediate, the overall rate of reaction is represented by the energy difference between the reactant and the highest energy transition state as shown in figure. The intermediate is very unstable and is transformed to products more rapidly that the reactants generate the intermediate, and this is the energy diagram of a two-step reaction with a less stable intermediate. Here delta F has, this shows free energy change between the reactants and first transition state, and this is intermediate, and delta F0 is the free energy change standard state between the reactant and product. This figure represents the reverse situation in a two-step reactions. In this case, the intermediate is very stable and the second step is rate determining, and here it is to be noted that the number of transition state in a multi-step reaction is always equal to the number of steps, and the number of intermediate is always one less than the number of steps. And this diagram shows two-step reaction with a stable intermediate, and here delta F1 is the free energy change between reactants and first transition state, and delta F2 is the free energy change between intermediate and second transition state. Here intermediates are normal covalent molecules or ions possessing a definite geometry and can be isolated in many cases. On the other hand, the transition state is not a normal covalent molecules or ions, as some bonds are partially broken whereas others are only partially formed. The properties of transition states are often studied by assuming that they resemble rather closely a real molecule that lies very close to it in energy content in a free energy diagram. This important generalization is a consequence of Hammond's postulates, which states that if two states, for example a transition state and an unstable intermediate, occurs consequently during a reaction process and have nearly the same energy content, their interconversion will involve only a small recognition of the molecular structure. Thus, The transition state may be described as reactant-like, product-like, or intermediate-like, depending upon the proximity of the former and any one of the latter. Now, a catalyst may be defined as a substance that increases the rate of a reaction without itself being consumed in the process. It combines with the reactant in the initial step and is regenerated at a later stage of reaction. A catalyst increases the rate of reaction by providing an alternative path from reactants to product with a lower energy transition state. In other words, the catalyst involves itself with reactants in such a way that the energy of the transition state of a catalyzed reaction is always lower than that of the transition state for the corresponding uncatalyzed reaction. Example, the catalytic effect of iodide ion on the hydrolysis of methyl chloride. Here, methyl chloride react with hydroxide ion in a one-step process and the rate depends on free energy change. Here methyl chloride is react with hydroxyl ion to give methyl alcohol and chloride ion. Addition of iodide ion to the reaction mixture provides an alternative path consisting of a two-step mechanism in which methyl iodide is an intermediate. Here methyl chloride react with iodide ion to give methyl iodide as an intermediate and chloride ions, and then these methyl iodide react with hydroxyl ion to give methyl alcohol and iodide ion. Since the iodide ion is both an excellent nucleophile and an excellent leaving group, the transition states of each step lower energy than that of the one-step process. It should be noted that the delta F0 of a reaction remains unchanged by the addition of the catalyst. Only the rate is increased, and figure shows these points. And here this is reactant and this gives product. This figure shows energy diagram for the uncatalyzed and catalyzed reaction. Uncatalyzed reaction shown by the broken line and the catalyzed reaction are shown by solid line, and here delta F1 is the free energy change for reactant and first transition state, and delta F2 shows the free energy change between intermediates and second transition state, and here delta F is the free energy change between the reactant and activated complex of uncatalyzed reaction, and here delta F0 is the free energy change at a standard state between reactants and products. Thank you.